Now let us start some problems, okay, of old gate. For example, a 3-phase 4-pole squirrel cage induction motor has 36 stator slots and 28 rotor slots. The number of phases in rotor is, okay. Basically, there is one question in ES and civils. If a stator is having 3 phases, how many number of phases should be there in the rotor? Okay. Basically, if it is a 3-phase stator, or maybe 10-phase stator, whatever it may be, from stator to rotor, actually from rotor side to stator side, are they interacting? Phases are interacting or poles are interacting? Number of poles will interact. Okay, so number of poles of stator and rotor should be same. Number of phases need not be same. Okay, for example, long back, maybe 50 years back. Okay, so if you see, our slip ring induction motors, at that time slip ring induction motors, stators used to be 3-phase, okay, but in rotor, we used to have only 2-phase. We used to have 2-phase only, such that 2 slip rings will be sufficient, no? And 2 brushes will be sufficient, no? Okay, and 2 resistances combinedly 1 box is sufficient, no? 1 box is sufficient, no? So we used to have that. Okay, in order to avoid 1 slip ring, 1 brush and 1 resistance combination, but recently afterwards, 3-phase, 3-phase load boxes developed, and 3-phase actually maintaining extra 1 slip ring doesn't matter much. So that's why we are maintaining 3 slip rings. So point here is very simple. Stator number of phases and rotor number of phases need not be same. But stator phases created number of poles, rotor created number of poles should be same. Okay, now coming to here. If it is a squirrel cage rotor. Now, for example, let us see for a single pole structure, how we have to analyze with respect to number of poles and number of phases. For example, if it is the stator, this is stator. Okay, stator is having 3 phases. Phase A, phase B, phase C. Now, the phase A is connected, phase B is connected, phase C is connected to supply. Under that condition, for example, 2 poles are created, N of stator and S of stator. 2 poles are created. And for example, they are rotating in this direction. Okay. Now, let us think of rotor. Okay. In my rotor, for example, if I have 4 slots. Okay, under that condition, for example, if you see here, it is at the center of the pole. How much will be the induced voltage here? Maximum, dot or cross, whatever it may be. I'm not saying whether it is dot or cross, but it is going to be maximum. So if it is positive maximum, it is going to be negative maximum. So combinedly, back-to-back connection, if you see phase A conductor or phase X conductor, back-to-back X dash, so it is closed. Now, whenever it is having maximum positive, how much is this induced voltage? 0. How much is this induced voltage? 0. So, maximum to 0, how much will be the time displacement? 90 degrees. Okay. Even if you think of sinusoid. Okay. So, sinusoid, maximum to 0, what is the angle? 90 degrees. Okay. So, whenever it is maximum, in this induced voltage is 0. Okay, so whenever this is maximum, in this induced voltage is 0, so how many phases are there as of now? 2. Why? Because these 2 are going to form 1 coil, these 2 are going to form 1 coil. So how many phases are there? 2 phases are there. So that's why, how many total number of slots are there in the rotor? 4. Per pole 2. Per pole 2. How many number of phases are there in the rotor now? Number of slots per pole. Per pole. Okay, we discussed about this in the theory also. But anyway, coming to the point, in order to confuse us, they have given 36 stator slots. Just to confuse you. Okay, so in order to confuse you, they have given 36 stator slots, which are useless. Forget about it. Now, how many number of rotor slots are there? 28. How many number of poles are there? 4 poles. So, number of phases okay, in rotor equal to number of slots per pole. Okay, so how many slots are there? 28. Per pole, how many poles are there? 4. So answer is going to be 7. Okay, now the same cannot be applied to intentionally wound winding. Okay, so what is intentionally wound winding? For example, stator. So you should not say 36 by 4. Is going to be number of phases in stator? No, because in stator we are providing 3 phases. Now, if it is in case of slip ring rotor also, in slip ring rotor our windings are intentionally wound. Okay, intentionally wound rotor, for example, intentionally wound rotor, I can what is intentionally wind either for 2 phases or 3 phases. But if it is squirrel cage, closed by its own, under that conditions, slots per pole is going to be like, with that we have to calculate. Now, let us see the second question. The power input to a 415 volts 50 Hz 6 pole 3 phase induction motor running at 975 rpm means 40 kilowatt. The stator losses they have given, friction and wind losses they have given, the efficiency of the motor is. Now, in this, previously in our power flow, we have seen exact power flow and we have seen approximate power flow like Steinmetz model. Okay, so are they, means in this particular question, are they following, or are we supposed to follow ideal one or approximate one? Let us see. See, for example, I have given some input to the stator. Okay, so if I give some input to the stator, from stator it is supposed to go to the rotor through the air gap. Now stator losses has to be detected. What are stator losses? Copper loss and core loss. Okay, and this is going to be air gap power. This is going to be rotor power input. From rotor power input, rotor copper losses has to be detected. Rotor core loss can be neglected because operating frequency under running conditions is going to be very less. So if I detect rotor copper loss, remaining is going to be power developed. From power developed, friction and windage loss or mechanical losses has to be detected. It is going to be shaft power. This is going to be ideal one. For example, if I remove this core here, if I keep it here, and if I add everything here as rotational losses, that is going to be approximate model. Now in the question, the stator losses are 1 kilowatt. The stator losses are 1 kilowatt. What does it mean? Stator losses are 1 kilowatt. Okay, so the moment stator losses are 1 kilowatt, which we have to follow, ideal one. Okay, depending upon the question. Now, what is the question? The efficiency of the motor is. Okay, so the efficiency of the motor they are asking. Now let us see the efficiency of the motor. Now what is the stator input? Stator input is 40 kilowatt. Now in this we have to detect 1 kilowatt. Is going to be the air gap power. Air gap power. So air gap power came. What is air gap power? 40 minus 1 is going to be 39 kilowatt. Okay, from 39 kilowatt, rotor copper losses has to be detected. What is rotor copper loss? If I think of this is PG, okay, S times PG is going to be rotor copper loss, or 1 minus S into PG is going to be the rotor power output to mechanical power developed. Okay, so in this case, so from here I have to detect S into PG. In the sense, developed power is going to be 1 minus S into 39 is going to be developed power. From here, friction and windage loss 2 kilowatt. Let us detect 2 kilowatt is going to be the shaft power. So efficiency is going to be PSH by 40 power input. That's it. Okay. So in this, just we have to find the slip. How much is the slip here? He is saying it is rotating at 975. What is the synchronous speed? 50 Hz 6 pole. Okay. So 120 into F by P. So 120 into 50 by 6 is going to give you 1000. Now slip is going to be NS minus NR 975 divided by 1000 is going to be 2.5%. So 1 minus 0.025 into 39 minus 2 is going to be PSH. So that is going to be, PD is going to be 38 point. So this 1 minus S into PG is going to be 38.025. So PSH is going to be, this is 2 kilowatt. So PSH is going to be 36.025 kilowatt. So efficiency is going to be 36.025 by 40 is going to be, efficiency I am going to get 90.06%. Okay, so 90% is going to be the answer. Now let us see one more question. In this question, if a 400 volts 50H star connected 3-phase squirrel cage induction motor is operated from a 400 volt 75H supply, the torque that the motor can now provide while drawing the rated current from the supply is. Okay, so keyword here is rated current. Okay, so if my rotor is having the same rated current, how my torque will be. Now before that, forget about induction motor and all, let us think of normal basic. For example, if I have N pole here, if I have S pole here, operating flux is going to be in this direction. Okay, now if I keep some current carrying conductor here, dot current carrying conductor, okay, so my flux will be in this direction. Okay, now net resultant of these two is going to be aiding, it will go aiding, opposing. For example, it is one flux line is flowing in this direction, red is flowing in opposite direction, so all fluxes will come like this. Now as I told previously, my flux lines will behave like a stretched rubber band. So all these flux lines are stretched. If I release, torque will be developed in this direction. Okay, so my torque will be developed in this direction. Okay, now for example, if black is reduced or red is reduced or both are reduced, net flux has to be reduced. Now he is maintaining same voltage, but frequency is increased. So normally if I maintain same voltage but frequency is increased, V by F ratio will be reduced. If V by F ratio is reduced, operating flux will be reduced. In the sense, my RMF, rotating magnetic field strength, black is going to be reduced. If black is reduced, so automatically my torque developed has to be reduced. So rated currents are rated. In the sense, red flux is same, magnitude of flux is same, but black magnitude of flux is reduced, so torque has to be reduced, decreases. Okay. In this question, a 400 volts 50H 30 HP 3-phase induction motor drawing 50 amperes. Actually about 30 HP I have to say one thing, that many students, the moment they see 30 HP, immediately they will try to consider that 30 HP and they will feel that it is working at 30 HP, it's none of our business. That rated capacity is 30 HP, it can operate at any load. Okay, so don't do that. Now 30 HP is the official given information, nameplate detail information, that's it. Okay, if they say if it is operating at full load condition and all, we will look into it. Okay, anyway, 3-phase induction motor is drawing 50 amperes current at 0.8 power factor lag. The stator and rotor copper losses are given. And the friction and windage losses are given. Core losses are given. The air gap power of the motor will be. Okay, now we have to think of whether we have to consider the ideal actual power flow or approximate power flow. Okay, so the core loss they have given separately, right? So and the core losses are 1200 watt. So approximate equivalent circuit need not be considered because core loss has given separately and friction and windage losses they have given separately. Okay, so the moment they have given friction and windage losses separately, core loss separately, indirectly they are saying that actual power flow you please consider stator, let us give power input. From that stator power input, let us remove or let us deduct stator copper loss, stator core loss is going to be air gap power. For example, combinedly if they give rotational losses, in the sense what are meant by rotational losses? Rotational loss is nothing but stator core loss and the mechanical losses. Under that condition, stator power input minus stator copper loss. Stator core loss will be at the end, no. So stator copper loss is going to be air gap power. Okay, so now let us see means actual power flow. What is asking? Air gap power. Okay, air gap power PG, air gap power. How to calculate? If you know power input, from input side how to calculate, output side how to calculate, let us see. For example, if you have stator power input, okay, so stator power input minus, okay, now stator losses will be there, stator core loss will be there, copper loss will be there in actual power flow. So stator copper loss, stator core loss is going to be power input to the stator minus stator loss is going to be air gap power. Now, from output side, if you want to calculate, for example, of course, output they did not give here. So, for example, shaft power input. Okay, so shaft power is going to be the output side plus friction and windage losses are mechanical losses. Okay, so shaft power plus mechanical loss is going to be mechanical power equivalent. So this is going to be PD, developed power. So developed mechanical power plus my rotor copper losses, because rotor core loss is neglected. So rotor copper loss is going to be rotor power input. Rotor power input is nothing but air gap power. Anyway, in this question, which type of information they have given? From input side they have given 50 amperes at 0.8 power factor lag. So let us use this equation. Okay. So in this equation, what is power input? Root 3. VL is how much? 400 volts. Into IL is how much? 50 amperes. Into 0.8 is going to be stator power input minus stator copper loss. Stator and rotor copper loss are 1.5 and 900 respectively. So 1500 stator copper loss minus stator core loss. Stator core loss they have given 1200 watt. So 1200 watt is going to be the air gap power. That air gap power is going to be 25.012 kilowatt. Okay, so in this, whatever may be the extra information, 900 watts is extra information of rotor copper loss. Okay, so air gap power minus rotor copper loss is going to be developed power minus mechanical loss is going to be shaft power. So in this question we have to use exact equivalent circuit. In this question, a 3-phase 440 volts 50 H 4-pole slip ring induction motor is fed from the rotor side. The stator of induction motor is connected to a variable resistance as shown. Okay, and 2 wattmeter. Basically, this induction motor is mechanically coupled to generator. Generator field is connected to 220 volts, and generator is connected with external resistance of 10 ohm. Okay, now 2 wattmeter method is used to measure the input power to induction motor runs at 1410 rpm. So the combination is running at 1410 rpm, and 2 wattmeter method is used to measure the power input here. Okay, so those wattmeter readings are 1800 watt and minus 200 watt. Okay, actually this particular question very intelligently they have given. I'll show you at the end why I said this statement. Okay, now the speed of rotation of stator magnetic field with respect to rotor structure will be. Okay, basically the combination is rotating at 1410 rpm. Okay, so in rotor fed induction motor analysis, I clearly told you how to analyze the things. Okay, so the speed of rotation of stator magnetic field with respect to rotor structure. Why to think of stator magnetic field with respect to rotor structure? So you are going to means the speed of rotation of stator magnetic field with respect to rotor structure. So let us think of rotor magnetic field with respect to rotor structure. Okay, so how much will be the frequency of the rotor? Is it SF or F? Okay, is it SF or F? It will be F only. Why? Because this is rotor. Okay, so in this rotor you are supplying 50 Hz. So in the rotor, how much is the frequency here? 50 Hz only constant. In the stator, frequencies will be SF. Okay, so because it is rotor fed, so in the rotor if you supply 50 Hz, okay, so frequency of rotor is going to be constant at 50 Hz. So if frequency is F, okay, if frequency is F, automatically it has to rotate at synchronous speed. If frequency is SF, it has to rotate with SNS. So the moment you are sitting on the rotor structure, automatically it should be NS. So 90 rpm will vanish. Okay, so the answer A will not be there, B will not be there. Okay, now see 1500 rpm in the direction of rotation, 1500 rpm in the opposite direction. Already you know the answer, opposite. Okay, why? Because in rotor fed my rotor has to rotate against to the direction of RMF. In rotor fed, machine analysis already we have done that. Now, let us see one more question. That is like, of course, this is a common data question actually. In the next question, what they asked, neglecting all losses of both the machines, the DC generator power output, the current through the resistance Rex will be. Okay. So, see here, though they said, like, neglecting all losses of both the machines. Okay, so can I neglect mechanical losses? Yes. Can I neglect copper losses? Yes. Okay, can I neglect in the DC generator is there no friction and windage loss or brush contact losses? All the losses can be neglected except rotor copper loss of induction motor, isn't it not? Because if rotor copper loss of induction motor is 0, torque will not be produced. Okay, so you please watch the videos of starting of induction motor. We clearly said that if rotor resistance is not considered, delta torque angle is going to be 180 degrees. Okay, if resistance is considered, if reactance is not considered, delta will be 90 degrees. If both resistance and reactance are considered, delta will be more than 90. Okay, so point here is very simple. We cannot neglect the losses of the rotor. Okay, now means here power input they have given 1800 minus 200 watt. So what is the total power input here? Total power input here is going to be 1800 minus 200 is going to be 1600 watt. Okay, so here 1600 watt is given. Now after detecting rotor copper loss, compulsorily rotor copper loss is, of course, now rotor became stator became rotor. Okay, so here now stator copper loss. Okay, because previously stator fed in the sense rotor copper loss, rotor fed in the sense it will become stator copper loss. Compulsory should be detected, remaining all completely will go. For example, if it is normal DC series motor or shunt motor or whatever it may be, synchronous motor, directly I can take 1800 minus 200 is going to be 1600 is going to come to here, we can say, because efficiency under ideal conditions of all machines will be 100% except induction motor. Okay, so means what we have to detect now, what is the slip now? Slip is going to be how much? Means it is rotating at 10 rpm. Means that synchronous speed should be 1500 because 50 Hz 4 pole. Okay, so how much is NS is going to be 50 Hz 120 into F by P is going to 1500 rpm. Okay, so what is the slip now? 1500 minus 1410 divided by 1500 into 100%. Okay, so you are going to calculate slip. That slip came down to 0.06 or 6%, 0.06. Okay, slip is going to be 0.06. Now, let us think of power input. Okay, is going to be 1800 minus 200, 1600. Now, what is the induction motor output? Is going to be 1 minus S into 1600. Okay, is going to be the induction motor output. Is nothing but the generator input, is nothing but the generator output. Generator output, it is going to come down to 1880 watt. I'm sorry, it should be 1504 watt. 1504 watt. So answer should be this. Now I will show. Just wait, why I said that they have given the question very intelligently. Okay, so if 1504 watt is being consumed by resistance, how much should be the current in the resistance? Basically, I square R equal to power. So I is going to be 1504 should be consumed by external resistance divided by 10 and the root is going to be 12.26 amperes. Will come. So option C should be right. Now, why I said they have given the question very intelligently. For example, if you think of 1800 minus 200 they have given, no? So for example, if you forget to take W1 minus W2 because W2 value is minus 200, if you forget to take, how much it will be? 1800, okay, plus 200. If you forget, actually we should not do that, but even if you consider this also, you will get one more option. Let us see. E is going to be 2000 watt. Okay, so 2000 watt, slip is going to be as usual 0.06. Now what is the power output of induction motor? E is going to be 1 minus 0.06 into 2000. E is going to be 1880 watt. Okay, so 1880 watt. 1880 watt. For example, if 1880 is being consumed by resistance, okay, so then I square R equal to 1880. So resistance equal to 1880 by 10 under root will come down to 13.71 amperes. Okay, so means like, if you are focused in the exam, you will get option C. If you forget to take minus, you will get option D. Okay, so actually IIT professors work hard actually to give questions. In this question, a 3-phase 400 volt 6-pole 58 squirrel cage induction motor is running at slip of 5%. The speed of stator magnetic field with respect to rotor magnetic field and speed of rotor with respect to stator magnetic field are. Okay, one thing like, in order to have continuous electromagnetic torque, basic concepts of rotating machines at starting we discussed. What did we discuss? In order to have continuous electromagnetic torque, compulsorily, like, stator magnetic field and rotor magnetic field should be stationary with respect to each other. Otherwise, continuous torque is not possible. Okay. And second condition was number of poles of stator and rotor should be same. Now, see, if stator magnetic field is rotating with ns, rotor magnetic field also should rotate with ns. Okay, rotor may not rotate at synchronous speed, but rotor magnetic field should be rotated at synchronous speed. That's what we discussed. Okay, so like, if you get any doubt, just go back and stator fed induction motor. Okay, just go there up to basic concepts. Now, means the speed of stator magnetic field with respect to rotor magnetic field should be 0. Okay, should not be 1000. Okay, now next thing is like, and speed of rotor with respect to stator magnetic field. Now the moment like, stator magnetic field and rotor magnetic field rotate at the same speed, now means speed of rotor with respect to stator magnetic field is not required with respect to rotor magnetic field. Okay, so for example, if stator is rotating with 1000, rotor is rotating with 950, rotor magnetic field will rotate at extra 50 rpm such that 950 plus 50 is going to be 1000. Getting my point, right? So rotor is rotating with 950, rotor magnetic field is rotating with 50. So what is the difference between these two? Minus 50. Okay, so see here, is it 5% slip, 6 pole? So what is the like, synchronous speed? Synchronous speed is going to be 6 pole. So synchronous speed equal to 120 F by P is going to be 1000 rpm. Okay, so it is rotating with 5% slip. So what is rotor speed is going to be 1 minus S into ns is going to be 950 rpm. So rotor is rotating with 950 and now rotor magnetic field is rotating with extra 50 rpm. Okay, so with respect to, see here, means speed of rotor with respect to stator magnetic field or with respect to rotor magnetic field. So with respect to rotor magnetic field 1000, it is rotating with 950 rpm. So answer should be minus 50. Yeah. Okay, now let us see one more question. A 4-pole induction motor supplied by a slightly unbalanced 3-phase 50Hz source is rotating at 1440 rpm. The electrical frequency in Hz of the induced negative sequence currents in the rotor is. Okay, one thing I have to tell you here, okay, means in our previous sessions also we discussed, like, in induction motor only sequence components has to be analyzed, and in induction motor only time harmonics has to be analyzed. In induction motor only space harmonics has to be analyzed. Why? Means to all the components, all the speeds, like, my rotor will, what do you say, interact. Okay, so in the rotor torque will be produced for positive sequence also, negative sequence also, of course zero sequence it will not. Okay, and like, for example, rotor, as our previous problem if I consider, for example, stator magnetic field is rotating with 1000, rotor is not rotating, so what is the relative velocity is more, but still torque will be produced. Now stator magnetic field is rotating with 1000, rotor is rotating with 950 for example. Okay, so what is the relative velocity between these two 50 rpm, then torque will be produced. Okay, so rotor, basically induction motor rotor will respond to all frequencies or all speeds. Okay, for example, if rotor is, stator magnetic field is rotating with 1000, rotor is rotating with 950. Okay, now means, for example, this is positive sequence 1000 means it is rotating here. Now negative sequence, phase sequence will be negative phase sequence, like phasor order will be reversed. So negative sequence will rotate in this direction. Okay, so of 1000 rpm, but rotor will rotate in the same direction, but for this 1000 rpm, for this particular rotor, because means the biggest thing in induction motor is independent of relative velocity between stator MMF and rotor, torques will be produced. Okay, so positive sequence, torques will be produced, negative sequence also torques will be produced. Okay, so means for all this, like in our harmonics also, one time they asked slip. Okay, fifth order fifth order time harmonic they have given, but many faculties felt that it is space and all, we will discuss at a later point of time. Anyway, rotor is rotating in this direction, positive sequence, negative sequence, rotor is rotating in the same direction only. So what is the main thing in induction motor? Slip. Okay, if we can calculate slip, torque produced can be calculated. For example, positive rotor is rotating in this direction. How to calculate torque slip should be known. For example, negative sequence, rotor is rotating in the same direction. If you know the slip, automatically torque can be calculated. So positive torque plus negative torque is going to be net torque developed in the induction motor. So in induction motor, slip calculations are very important, because independent of relative velocity between stator magnetic field and rotor, torque will be produced. Okay, anyway, this is 1440 rpm. So for example, if stator magnetic field is rotating in this direction with 1500 rpm, rotor is rotating in the same direction with 1410 rpm, 1440 rpm. Now this is positive sequence. Now positive sequence is going in this direction. Now negative sequence will rotate in opposite direction with 1500 rpm. So what is the relative velocity between rotor and negative sequence? Is going to 1500 plus 1440. So for example, slip, if you calculate, what is slip actually? Ns minus Nr by Ns. Now Ns plus Nr. Okay, so this is going to be slip in the negative sequence. Okay, so Ns plus Nr. So Ns plus, what is Nr? Ns into 1 minus S of positive. Okay, divided by Ns. So this is going to be 2 minus S of positive is going to be slip of negative. Okay, because 1 plus 1 minus 2 minus S. Okay, so if you calculate slip, for example, if I try to calculate slip for negative sequence is going to be 1500 plus 1440 by 1500. Okay, calculate the slip. Now what is frequency of rotor induced voltages? Frequency of rotor induced voltage is going to be S times frequency of stator. Okay, so calculate slip and add 50 into multiplied by 50, because stator frequency is 50 Hz, you are going to get 98 Hz. Okay, or directly calculate 1500 minus 1440 divided by 1500, you are going to get S of positive. 1 minus of that into 50 Hz is going to give you 98 Hz. Okay, now next thing is, let us take one more problem. An 8-pole 3-phase 50 Hz induction motor is operated at a speed of 700 rpm. The frequency of the rotor current in the motor is. Okay, so let us calculate 8-pole 3-phase 50 Hz. Let us calculate synchronous speed. Ns equal to 120 F by P is going to give you 750 rpm. Okay, now let us calculate slip. Slip is going to be Ns minus Nr by Ns. Okay, negative sequence and all is not there, it is stator fed only, nothing is actually this is a very small question. That is BTech level. For BTech also it's actually very normal question. This is going to be 750 minus 700 by 750 is going to be the slip. Okay, now what are stator frequency? So what the frequency of the rotor current? Frequency of the rotor current equal to S into F1. S you calculated here into F1 is 50 Hz. Okay, it will give you 3.33 Hz. 3.33 edge. Actually, it is a numerical question. Okay.